When you picture the future of renewable energy, your mind probably jumps straight to, I don't know, vast, scorching desert landscapes.
Right. Acres of glass just soaking up the blazing sun.
Exactly. Or maybe the bright, sunny rooftop of a suburban home. But what you probably don't picture is a howling sub-zero blizzard.
No, definitely not. I mean, it feels completely counterintuitive, right, to associate solar power with extreme cold and months of total darkness. Yet that is precisely the assumption we are challenging today.
Yeah, so welcome to our deep dive. I'm so glad you're here with us, the listener, because today we are taking on this fascinating new obsession of mine.
This is a really cool topic.
It really is. The mission for today is to find out if solar power, a technology we fundamentally associate with heat and direct sunlight, can actually survive and, more importantly, thrive in the darkest, coldest, and snowiest places on Earth.
Which is a tall order.
It is a massive order. And to answer that, we are looking at some incredibly rigorous data. We're pulling directly from a highly detailed, high-resolution techno-economics study. It's by researchers at LUT University in Finland.
Oh, they do some great work.
They really do. And I want to give you the exact title of the study right up front. It's called Prospects and Competitiveness of Solar Photovoltaics System Setup Portfolios in the Arctic and Subarctic Region.
Right. And what makes the research coming out of LUT University so compelling is that it completely shatters the myth that the extreme north is just, a dead zone for solar energy.
Because that's what we've all been taught, right?
Exactly. We've long operated under this assumption that deploying solar panels in the tundra is just a fool's errand because, well, they'll simply get buried in snow.
Right, they just become expensive snowdrifts.
Yeah, exactly. But the underlying issue wasn't the geographic location. The issue was actually the geometry.
Geometry, okay.
Yeah, by simply changing the physical orientation of how a solar panel stands, we might be unlocking a completely new energy frontier.
Okay, let's unpack this. Because to understand why the findings in this study are so groundbreaking, we have to examine why the current methods have been failing up there in the first place.
Right, we have to look at the baseline.
Yeah. So we are looking at the Arctic and subarctic regions. Specifically, the study defines this as the areas above 50 degrees north and 66.5 degrees north latitude.
And just for context, these are some of the most climate-sensitive ecosystems on the entire planet.
Oh, yeah. They are warming significantly faster than the global average.
Which creates a deeply ironic and, frankly, problematic energy situation.
Yeah.
Because a lot of these remote communities in these latitudes, they aren't connected to some massive centralized power grid.
Right. They can't just plug in.
No. They rely really heavily on diesel generators. They literally have to ship or, in a lot of cases, fly in dirty fossil fuels just to keep the lights and the heat on.
Which is, it's economically draining, but it's also environmentally damaging in the exact location that is most vulnerable to climate change.
Exactly. It's a vicious cycle.
And the logistics of getting that diesel up there are just getting harder every year. Ice roads are melting earlier in the season, which makes fuel deliveries incredibly expensive.
Yeah, the supply chains are literally melting.
Right. So the obvious thought is, well, let's install local renewables, like solar. But historically, when engineers try to use standard solar panels, what the industry calls fixed tilted panels.
Right, the ones you see angled up toward the equator on people's roofs.
Yeah, exactly. When they use those, they face massive mechanical and environmental hurdles.
Because the environment actively works against that specific geometry.
How so?
Well, first, you are dealing with a very low sun elevation. The sun doesn't pass high overhead like it does at the equator. It hangs really low on the horizon.
Oh, right, because of the curvature of the Earth.
Exactly, meaning a tilted panel is mostly pointing at empty sky rather than actually intercepting the sun's rays. And second, you have the absolute killer for conventional solar engineering up there.
Snow accumulation.
Yep, snow.
I like to think of it like this. Relying on standard tilted panels in the Arctic is like trying to catch rain in a bucket that's already full of ice. It just doesn't work.
That is a perfect analogy.
The snow just piles up on that 30 or 40-degree incline. And the data in this study gives some really striking numbers on the consequences of that geometry.
It's pretty grim for traditional panels.
It really is. For optimally tilted panels in Sweden, the study found they lose up to 14.7% of their power generation strictly from snow just sitting on top of them.
Which is a huge hit to efficiency.
Massive. The panels literally just become high-tech snowdrifts. And that's not even counting the dirt dirt and the grime. They found that soiling alone causes another 1.5 to 4.5% annual yield loss across the Nordics.
Wow. So this raises an important question for energy grid designers.
Right.
If tilted panels just act as snow catchers, how do we capture the sun without losing all that efficiency?
Right. What's the alternative?
Well, down in lower latitudes, the standard solution to maximize efficiency is to use robotic tracking systems, specifically horizontal single-axis tracking, or HSAT.
Okay, HSAT. And those are the ones that actually move, right?
Yes, they are these mechanical mounts with motors and sensors that physically tilt the panels to follow the sun as it moves across the sky.
Which, I mean, that sounds like a great way to maximize those low-angle rays in the Arctic.
In theory, yes. But applying that to the Arctic seems like a mechanical nightmare, and it is.
I can imagine.
At minus 30 degrees Celsius, the physical realities of moving parts completely change. Lubricants freeze solid.
Oh, wow.
Yeah, metal components become brittle and contract. The motors that drive those tracking mechanisms, they frequently just fail under the stress of freezing and thawing cycles.
So they just snap.
Pretty much. They are incredibly expensive to install, and they are simply too fragile to survive the brutal mechanics of the extreme north. So we are basically left with a paradox here.
Right. Conventional tilted panels get buried in snow, and dynamic tracking panels just break in the cold. And that leads us to the elegantly simple geometric pivot that this study introduces. Since conventional shapes fail in a battle against gravity and snow and mechanical stress, the researchers modeled a completely different setup.
And it's so smart.
It is. It's called the East-West Vertical Bifacial Panel.
Right. And when you analyze the physics of it, it is just a wonderfully pragmatic concept.
For you listening, picture this setup. Instead of a panel tilted back like a lawn chair, imagine a panel standing straight up, perfectly perpendicular to the ground, almost like a fence.
Just a wall of glass.
Right. And instead of facing south toward the equator, it faces east and west. And the key technological component here is that it's bifacial.
Meaning it has active solar cells on both its front and its back.
Exactly. It captures light from two directions simultaneously.
What's fascinating here is the sheer cascade of physical advantages this vertical setup creates, starting with the most fundamental force gravity.
Oh, of course.
Right. When a panel is standing perfectly straight up, the angle of repose for snow is zero.
Because there's no surface for it to land on.
Exactly. Snow cannot physically pile up on a vertical surface. It just falls straight off. Gravity basically performs the cleaning and maintenance for free.
That's brilliant.
It is. That means zero winter downtime from snow accumulation. It completely eliminates that 14.7% yield loss we saw with the tilted panels in Sweden.
Okay, but the advantages go beyond just shedding snow, right? This is where the environment itself actually becomes an asset rather than a liability, and it's specifically because of the snow on the ground.
Yes, we were talking about the albedo effect.
The albedo effect.
Right, so albedo is a scientific measure of how much light a surface reflects. Dark asphalt, for example, has a very low albedo. It absorbs light and turns it into heat.
Which is why roads get so hot in the summer.
Precisely. Fresh white snow, on the other hand, has an exceptionally high albedo. It often reflects 80 to 90% of the sunlight that hits it.
Wow.
The scope basically acts like a giant, naturally occurring mirror.
Okay, so imagine being inside a mirrored room with a single light source. The light bounces off the floor and hits you from literally all angles. With a vertical panel, the sun hits one side directly.
Right, the east or west side.
But the sunlight is also hitting the bright white snow all around it and bouncing back up. And because the panel is bifacial, that rear face is actively converting all that free, reflected light into electricity.
It's free energy. And the performance data modeled in this study quantifies just how effective that bounced light really is.
What did they find?
Well, when evaluating locations in the extreme north, specifically above 75 degrees north latitude, these east-west vertical setups only show a tiny 0 to 13% yield deficit compared to those highly expensive, fragile robotic tracking systems.
Wait, really? Just 0 to 13% less than a robot tracker?
Yes, just from standing up and catching reflections.
That is wild. Meanwhile, the study notes that the standard fixed-tilt panels in those exact same locations are suffering massive yield deficits. They produce up to 37.3% less energy than the trackers.
Because they're covered in snow and facing the wrong way.
Right, so standing the panel completely upright is fundamentally superior when you factor in the snow shedding and the albedo.
It absolutely is. And if we connect this to the bigger picture of planetary geometry, standing the panel up is actually the absolute perfect shape for capturing the low-angle sun.
Because the sun doesn't rise very high.
Right. In the Arctic spring and summer, the sun doesn't arc high overhead. It just kind of skims along the horizon. It rises in the east, sweeps low across the sky, and sets in the west.
So a vertical fence facing east and west intercepts those low rays perfectly, right in the morning and right in the evening.
Exactly. Catches it right on the broadside.
And this is a big but surviving the winter and catching the light doesn't really matter if you're generating power at the wrong time of day.
Oh, this is the grid problem.
Yes. Anyone who works with the power grid will tell you that the timing of electricity generation is just as critical as the overall volume. We have to move from just physical survival to actual grid strategy.
Which introduces the challenge of the daily power curve. The energy grid, it requires power when people are actually awake and consuming it.
Makes sense.
This typically creates a demand spike in the morning when people wake up and turn on appliances, and another spike in the evening when people return home.
Right.
But the inherent flaw with standard south-facing tilted panels is that they generate this massive, narrow spike of electricity right at solar noon, which is exactly when demand is often at its lowest.
Because everyone's at work or school.
Exactly.
That mismatch is exactly why the industry covets those robotic tracking systems we talked about earlier. By following the sun from east to west, the trackers provide a smooth, wide curve of power that stretches across the entire day.
Right. They perfectly match human consumption habits.
But since those mechanical trackers break in the ice, the researchers needed to find a way to replicate their output using stationary equipment. This study introduces a novel methodology to quantify how well stationary, completely non-moving panels could mimic the daily power curve of the robotic trackers.
The engineering goal was essentially to replicate the dynamic performance of robotic hardware using only static geometry.
And here's where it gets really interesting. The breakthrough they found is just staggering. They discovered that if you use a 50-50 mix,
Meaning half of your solar portfolio consists of standard fixed tilted panels.
and the other half consists of the vertical standing panels, if you do that, it almost perfectly replicates the daily output curve of the moving robotic trackers.
It's amazing. Think of it like a choir covering different octaves to create a full sustained chord.
Oh, I like that.
Yes, so the standard fixed panels sing the midday note. They capture whatever high sun is available. Meanwhile, the vertical panels sing the morning and evening harmonies, capturing that low-angle horizon light.
And together, they create this beautiful, widened production profile that sustains grid power throughout the entire day.
Yes.
But, it's hard to believe a static 50-50 mix can genuinely replicate a complex, moving tracking system. Like, how does the math on that actually hold up without any moving parts?
Well, the researchers validated this using a statistical measure called the coefficient of determination, or more commonly, R-squared.
R-squared.
Okay, yeah. This metric basically measures the proportion of the variance in one variable that is predictable from another. So essentially, it tells us how perfectly the mixed static panels mimic the tracker's exact hour-by-hour output.
And the numbers the study produced are massive. Between 60 degrees north and 75 degrees north, this 50-50 portfolio achieves a diurnal correlation with an R-squared of 0.86 to 0.96.
Which is exceptionally high.
Right. For context for you listening, an R-squared of 1.0 would mean it is an absolutely identical clone.
A perfect match.
Yeah. So reaching 0.96 means the power curve is virtually indistinguishable from a hyper-expensive robotic tracking system.
You are basically looking at a triumph of spatial arrangement over mechanical complexity.
I love that phrase.
We are solving a dynamic mechanical problem with a static geometric solution. We're completely eliminating the motors, the sensors, and all the maintenance costs associated with moving parts in sub-zero temperatures.
Okay, so we have a system that survives the snow, it catches the albedo glare, and flawlessly mimics the best tech on the market.
Yep.
But that brings us to the ultimate decider for literally any new technology, the economics.
Ah, yes. The bottom line.
Always. You can design the greatest geometric system in the world, but if a remote community can't afford to build it, it stays in the laboratory. We have to talk about the economics of the tundra.
Well, in energy economics, we evaluate viability using the levelized cost of electricity, or LCOE.
LCOE. Got it.
Right. Instead of just looking at the upfront sticker price of the solar panels, LCOE calculates the true cradle-to-grave cost.
So everything included.
Everything. It factors in the cost of building, operating, and maintaining the power plant over its entire 25 to 30-year lifetime, and then it divides that by the total energy it will ever produce.
Okay.
It basically tells us the exact cost to generate 1 megawatt hour of electricity.
And when this study ran the LCOE numbers across the entire Arctic, the results completely flipped our traditional understanding of solar costs.
They really did.
The reference portfolio, which is the standard fixed-tilt way we do things now, sits somewhere between 18.2 to 51.7 euros per megawatt hour in these regions. But when evaluating extreme northern locations, specifically above 75 degrees north, the vertical configuration actually reduces those costs by anywhere from 1.4% to 14.0%.
Which proves the vertical panels aren't just a physical adaptation. They are actively driving down the cost of energy generation in these environments.
To make this concrete, let's look at the logistical reality of some specific locations modeled in this study in Utqiagvik, Alaska.
Oh, which is incredibly remote.
So remote, it's on the northern coast where construction and maintenance logistics are just astronomically expensive. But there, vertical solar is 9% cheaper than traditional fixed-tilt solar.
That's a massive saving for a community like that.
Huge. And when forecasting out to the year 2050, the study shows vertical setups remain the absolute lowest cost solution in incredibly harsh places. Places like East Bajan Island in Canada and Murmansk in Russia.
Which means, for you, the listener, the implication here is profound. Vertical solar in the Arctic is no longer just a niche science experiment.
No, not at all.
It is the most economically viable and rational path forward for these specific latitudes.
Right.
Because it avoids the mechanical failures of tracking systems and it leverages the albedo of the snow. It actually beats out coal and nuclear in terms of lifetime generation costs.
That is just incredible to think about, but I have to bring up the obvious limitation.
Oh.
Because anyone looking at a globe will spot the elephant in the room here. We're talking about solar power in the Arctic. What about the months of complete, total darkness in the Arctic winter?
The polar night.
Yes. The sun literally does not rise for weeks at a time. The albedo effect and vertical geometry, none of that matters if there are 0 photons hitting the panel.
That is the crucial reality check for any solar technology at high latitudes. Solar power cannot operate in a vacuum. It has to be integrated into a broader meteorological ecosystem.
And that brings us to the ultimate tag team.
I love this part.
It's so cool. The study didn't just look at solar in isolation. It analyzed how solar interacts with other local renewables. And it proved that solar is the exact missing puzzle piece for wind energy.
Exactly. When you study the atmospheric dynamics of the Arctic, you find a distinct and really powerful thermal pattern. Wind is primarily driven by temperature gradients.
Meaning differences in temperature.
Right, differences in temperature between different masses of air. So during the dark winter months, the massive temperature difference between the freezing polar vortex and the warmer lower latitudes, well, it drives fiercely strong, consistent winds.
Okay, so lots of wind in the winter.
Tons. But during the bright summer months, when the sun is constantly shining and warming the Arctic, that thermal gradient weakens, and the winds die down significantly.
The researchers mapped out this complementarity perfectly using Murmansk, Russia, as an example. The meteorological data here is just fascinating. In Murmansk, onshore wind turbines generate a massive 420 full load hours in the dark, freezing month of February.
420 hours, that's a lot of power.
It is. But by July, when the air is stagnant, that wind generation plummets to just 61 hours.
Meaning, if a remote community only relies on wind turbines, they face a severe energy deficit every summer,
Right.
which would force them right back onto those dirty diesel generators.
But look at what happens when you introduce a mixed solar portfolio, specifically that 60% fixed tilted and 40% vertical solar PV mix we talked about.
Right, the mix.
In that pitch black month of February, the solar portfolio only yields 10.7 hours.
Barely a trickle.
Barely a trickle. But in July, when the wind turbines are barely turning, that exact same solar portfolio skyrockets to 149.5 hours of generation.
They fit together like perfectly interlocked gears.
They really do.
The natural atmospheric cycles basically dictate that as the wind production curve drops, the solar production curve rises to catch the load, and vice versa.
So what does this all mean? It means the problem of the dark Arctic winter isn't actually a problem for solar, because solar doesn't need to work that shift. Wind works the night shift during the winter, driven by those thermal gradients. And vertical solar works the day shift during the summer, driven by the constant low-angle sun.
It's a perfect partnership.
It is. Together, they create a balanced, year-round renewable energy grid. And that drastically reduces the need for massive expensive battery storage or, importing diesel fuel.
It creates a localized, self-sustaining loop. We can provide energy security to these remote communities using the very extremes of their harsh environment to our advantage, rather than constantly fighting against the elements.
It's such a brilliant shift in perspective. Well, we have covered an incredible amount of ground today. Let's recap the journey. We started with the logical assumption that the extreme north is just too snowy and dark for solar power.
Which, as we saw, was a geometry problem, not a location problem.
Right. We saw how standard tilted panels act like shelves for snow, losing significant efficiency, and how dynamic robotic trackers are simply too brittle for sub-zero climates.
But then, by analyzing the physics of a simple geometric pivot, standing double-sided panels up like fences, we utilize gravity to clear the snow.
Free maintenance.
Exactly.
Yeah.
We leverage the albedo effect to catch the intense glare bouncing off the white ground, and we perfectly intercept the low-angle horizon sun.
And then we explored how mixing those standing panels with flat panels magically mimics the power curve of a robotic tracker, solving a complex mechanical problem with just static geometry.
It really is elegant.
It is. We saw that in places like Alaska and Canada, this significantly lowers the levelized cost of electricity. And finally, we saw how vertical solar forms the ultimate tag team with winter wind power, perfectly balancing the grid through the seasons.
This approach truly represents a paradigm shift in energy engineering. But, if we connect this to the broader implications outside of the Arctic, it raises an important question for how we design our own environments.
Oh, okay. Where are you going with this?
Well, we spent this entire time talking about the extreme north as if it's an isolated laboratory, right? But if vertical bifacial panels are this effective at catching reflected light, shedding snow, and producing a stable power curve in the harshest conditions on Earth.
Imagine the possibilities when we bring this tech south to lower latitudes.
Exactly.
Right, because we tend to assume that advanced, specialized tech is only for extreme environments. But the Arctic might actually be a beta test for redesigning our own cities.
Absolutely.
Imagine integrating vertical solar panels as noise barriers along our major highways. Just utilizing that massive amount of unused linear space.
Oh, that's a great application.
Or wrapping the vertical sides of skyscrapers. Or implementing agrivoltaic.
Right, where vertical panels stand like fences in farm fields.
Yeah, generating power right alongside growing crops without taking up massive amounts of acreage.
Exactly. The potential is just enormous when we stop thinking of solar farms as flat, isolated fields and start thinking about turning the existing infrastructure we already have into invisible, highly efficient power plants.
Now, that is something to think about. I want to give a massive thank you to you, our listener, for joining us on this deep dive.
Thanks for listening.
And a quick reminder that all of the complex data, atmospheric modeling, and economic insights discussed today were drawn directly from the comprehensive research, prospects, and competitiveness of solar photovoltaic system setup portfolios in the Arctic and subarctic region. Until next time, stay curious.